Okay, video lecture 2.5. This is our last video lecture for chapter 2. And this is about certainty and uncertainty in data. And I hope you're seeing the uncertainty in this picture. What we mean by certainty and uncertainty in data has to do a little bit with how confident we are with our particular data. I want to start out by iterating that there are two types of data. And if you were to obtain some data, you could obtain it via an experiment, or you could obtain it via research. And if it is data that comes by the use of an experiment, by the use of a lab, it's experimental data. This is a value obtained in a lab setting. If it is accepted data, it's a value that is accepted to be true or is known to be true. This we often call as the ideal value. And an ideal value is what we would know it to be or what we would accept it to be. And experimental data is what we find in our experiment. Our experiment rarely matches the accepted data. Now, depending on where they match up, we have different ways to look at this. Obviously, we have accurate and inaccurate. A 100-gram sample that we know is 100 grams. We test it on the scale, it measures up. So that means our experimental data is really matching the accepted data. On the other side, the experiment 98.89, that's off by more than a tenth of a gram, or I'm sorry, more than 1 gram. And that's showing that it is the experimental data is not close enough to the accepted data in that case. And so again, the experimental value is what we obtain, and the accepted value is what we already know to be true. This gives us an equation for what we call percent error. Ultimately, we're saying how many percentage points are we off? Are we away from what we know that it should be? And so our equation now is the accepted, which is what we know to be true, subtract away what we find in our experiment, make that one value, and then divide that again by the accepted. What we need to think of here is the accepted is kind of like the total. If you were going to calculate your grade, you take how many you got right divided by the total. This is sort of like that, but it's not how many you got right, it's how many you got wrong. It's how far off you were, and that's what we mean by error there. This is another way that the equation has been put as experimental minus theoretical. Theoretical and accepted really mean the same thing. Here they're showing a different order, but if you notice one thing in either of these equations, it has everything in absolute values, which means it doesn't matter if you have 2 minus 3 or 3 minus 2. They'll both be 1 because of the absolute value there. Another way that this equation could be presented is measured, which is experimental, minus the accepted there. So there's a few ways you might see this presented. I will be presenting it the way you see the first one that I had listed there. We'll use that equation to find percent error. We'll also look at some properties of measurements. We can look at accuracy and we can look at precision. Now when we look at these two, they mean two very different things. If we are accurate, we are hitting the bullseye. What we need to think of the bullseye as being is that true value, that accepted value. So accuracy is how close measurements are to the accepted value, or what we accept to be true. That's our target, that's our bullseye. That's accuracy. Now with precision, if an instrument is precise, that means it's going to measure the same every time. And when we say precision with our measurements, we're saying how close each of those measurements are to each other. What this really means is how tight the grouping is. If you have one measurement at 12.5 inches and another at 14.5 inches and another at 10.5 inches, you've got a spread there. But if you've got 3 measurements all within 1/2 an inch, then your precision is much tighter. Here's our example here. I love to shoot guns, and so if we were shooting a rifle at a target, we could look at each of these scenarios. I want to look at the bottom right hand corner. We're hitting the bullseye. All 4 of those shots are inside that inner circle. That means it's accurate. All 4 of those shots are also very close together, very tightly grouped. That means it's also precise. If you want look at the one just to the left of it, we see 4 still quite close together. But none of those 4 are particularly close to that center bullseye. So they're not really that accurate because they're off to the side, but they are tightly grouped, so they are precise. If we look above that, we see 4 that are spread out and only 1 that's at all close to the center bullseye. So it's not that accurate, at least as a collection. One of them's accurate, but all 4 of them are really not accurate, and they're not precise because they're not close together. Now if we see the next one in the upper right hand corner, we notice that 3 of the 4 are in that secondary gray circle, and the other one's pretty close. So it's more accurate than either of the 2 on the left, but it's not precise because those shots are still not that close to each other. Another picture here, we see the same idea with darts. You see the first one is terrible accuracy, also spread out, so also terrible precision. We see the next one is they're all bundled up close together, so there's good precision, but not close to the target. Then we see the third one, all in the bullseye looks good, but they're still fairly spread out. So it's not great precision, but it's pretty good accuracy. And then we see the last one, all 3 bunched together in the bullseye is accurate and precise. So we'll need to be able to identify those with numbers as well. And we'll talk about that a little bit more in class. The last thing I want to mention here is what we call proportionality. And if you hear proportion or think of the word proportion, hopefully you're thinking of fractions, and in a way it does have to do with that. It's really comparing things a little bit. So we have 2 main types of proportionality. Let's start with the definition here. We have direct proportionality. Direct means a direct connection, means that if one variable changes, the other variable changes in a similar way, or we say the same change. And so what we're saying here is that if I increase the mass, I will increase the density. If they both increase, it's direct proportionality. It's the same type of change. Here we see a graph. This is direct proportionality, because if you go anywhere on that graph, and then you are on that blue line, and then you move up the line, both XY coordinate will have increased. So it is that same change there. Now if we look, and the equation, by the way, for the graph is y equals x. If x goes up, y goes up as well. And so you do have that direct proportionality there. Now I'd rather us see this in an example. D equals m over v. Density equals mass divided by volume. If the mass goes up, so does the density. Therefore, D, which stands for density, and m, which stands for mass, are directly proportional. If one goes up and the other does the same thing, then they're directly proportional. Indirect proportionality, or sometimes called inversely proportional, variables will have opposite change. It's a change in one variable results in a different change in another variable. It's not saying they change in exactly the same amount, it's saying how they change is different. And so here we see a different equation, and notice the inverse of what y equals. In the top one, y equals x, and the bottom, y equals 1 over x. We've taken x and we've inverted it to where it was on the denominator instead of the numerator. So here we see a different graph. If we move along the green graph, starting up high and then moving to the right, we are dropping in the y coordinate as the x coordinate goes up. So we have an opposite change in the 2 variables. Let's look at a different equation. This is a pressure equation that we'll see later on. Pressure equals force divided by area. Looks very similar to density equals mass over volume. If the area is reduced, meaning if we shrink the area, pressure actually increases. So therefore P for pressure and A for area are indirectly, or we can also say inversely proportional, because they have an opposite change there. You'll need to be able to identify these variables by looking at them in the equation. We'll go over some kind of hints to that a little bit in class next time we see each other. And he must be talking about a measurement with his hands there, but regardless of what he's doing there, we are done with chapter 2.